Okay, welcome back. Like I said, let's quickly look at ideal solutions, module 3.2, CHE 311, physical chemistry 2. I still remain Professor Engineer JC Igwe. Now, the outline of the lecture: introduction, ideal solutions, vapor pressure of ideal solutions, properties of truly ideal solutions. Then we'll use an illustration and conclude. Introduction. An ideal solution is defined as a solution in which there are no intermolecular forces of attraction. You see, we talk about no intermolecular forces of attraction, but you wonder how possible that will be for an ideal, for any solution, that there is no intermolecular force of attraction between the solute and the solvent. Of course, as we shall see, the only way that can be approximated is when the number of moles of the solvent is far greater than the number of moles of the solid. Because if it is concentrated, then of course it's just like when you have a class. In your class, many of you are seated down, and then somebody will say that nobody is touching each other. No. The only way that can happen is probably you are meant to sit far away from each other. That will approximate to an ideal solution. For ideal solutions, the activity coefficient is equal to 1, that is equal to unity, and the concentration can be used in place of activity. If we still remember our Lewis fugacity rule, which says that the concentration is equal to the fugacity coefficient, multiplied by the pressure, or the activity is equal to the activity coefficient multiplied by concentration. If we're talking in terms of gas, we use fugacity. So activity coefficient here, when it is for ideal solutions, activity coefficient will be equal to 1. And when that is equal to 1, then it means that the activity will be equal to concentration. So that's why we can interchange concentration with activity. Also remember, we have looked at concentration and activity. Other thermodynamic functions that describe completely the conditions for ideal solutions are the change in enthalpy of mixing, the change in internal energy of mixing, the change in volume of mixing. All must be equal to 0 for us to have an ideal solution. We will still see that in the properties of truly ideal solutions. Ideal solution is a solution in which the total vapor pressure is governed by Raoult's law. And Raoult's law is given by equation 1 there, that the total pressure is equal to x1 p1 raised to power 0 plus x2 p2 raised to power 0. x1 is the mole fraction of the solvent. P1 to power 0 is the pure vapor pressure of the solvent. X2 is the mole fraction of the solute, and P2 to power 0 is the pure vapor pressure of the solid. So you see that this is similar to Dalton's partial pressure. X1 P1 naught is the partial pressure of the solvent, while X2 P2 naught is the partial pressure of the solid. When we add that two together, it gives us the total vapor pressure, which gives us Raoult's law. Now, for two components, P1 is equal to X1 P1 naught, and P2 is equal to X2 P2 naught. So from Dalton's law, we'll add the two. P total is equal to P1 plus P2. So we substitute X1 P1 naught plus X2 P2 naught. And then we'll simplify. And when we simplify, we'll get PT as equal to X1 into P1 naught minus P2 naught plus P2 naught. The partial pressure Pi of the ith component in the vapor in equilibrium with the solution is given by Pi equal to Xi Pi naught, and that's Raoult's law. Assuming the vapor behaves like a perfect gas, then the ith component chemical potential will be given by equation 4. Therefore, a more appropriate definition of an ideal solution is therefore given by equation 5. That is, the chemical potential of the solution is equal to the chemical potential of the component in the liquid plus RT ln mole fraction of that component. This equation can also be used to derive Raoult's law. Now, solutions which approach ideality or whose behavior approximate to ideal solutions are only liquid mixtures whose components are very similar. So when they are very similar, for instance, if we look at something like benzene and methylbenzene, which I have used to generate this figure here. This figure is showing us the variation of the vapor pressure with the mole fraction for the two mixtures. P1 is the vapor pressure against the mole fraction x1, and then P2 is the vapor pressure against the mole fraction x2. Whereas P subscript T gives us the variation of the total vapor pressure. If we look on the right of that graph, we'll see P2 to power 0. That is the maximum pressure attainable, which is the pure vapor pressure of component 2. And by the left, we'll see P10, which is the pure vapor pressure of component 1. So all solutions that obey Raoult's law will have this chart. But we also have negative and positive deviations from Raoult's law, where the P total will no longer be a straight line. Properties of truly ideal solution. Like we said, we now see equation 6, 7, 8, 9, and 10 gives us the properties of truly ideal solution. What value the delta G will give, what value the delta S will give on mixing, what value delta H must be 0, delta V must be equal to 0, and of course delta E must also be equal to 0. And then for ideal solutions of solids in liquid, we'll use what we call the ideal solubility equation, equation 11, to find the mole fraction of the solid. Okay, and that's an illustration using the ideal solubility equation. Now we're given that naphthalene melts at 353.2 and its heat of fission is given. Applying the equation, estimate the ideal solubility of naphthalene in any liquid at 298 K. We use the equation and substitute. Of course, R is our gas constant, and we are given delta H fuse, that is the heat of fission for naphthalene, and we substitute, we'll get X as equal to 0.30. We've looked at introduction to ideal solutions, vapor pressure of ideal solutions, properties of truly ideal solution, and an illustration. Thank you very much, and I hope to see you in Module 4. Thank you.